The alternating series test, part 3. Consider a sub n a sequence of positive, finite, and decreasing terms that go to 0 as n goes to infinity. Then, the sum of a sub n times -1 to the n is an alternating series, and it will converge. Furthermore, the error associated with an approximation is always less than or equal to the first left-off term. Let's look at our first example. Let f of 1 equal -2, f prime of 1 equals 4, and then the nth derivative of f at 1 is given by the formula -1 to the n times n squared times 2 to the n for all n greater than or equal to 2. Write the fourth degree polynomial approximation to f of x, centered at 1, of course, by implication in what's given. So we want to find t sub 4 of x. Recall that t sub 4 is one of the main notations indicating a polynomial approximation, the 4 being the fourth degree. So t sub 4 of x is f of 1, -2, plus f prime of 1 times x minus 1. And then, let's see, f double prime, so when n equals 2, we have -1 squared, which is positive. Don't worry about these consecutive terms both being positive, because all the rest of the terms will alternate based on the -1 to the n. So I have -1 squared, which is positive, and then n squared, or 2 squared, times 2 to the n times x minus 1 squared, and don't forget to divide by 2 factorial. N equals 3. We have -1 cubed, which is negative, and then we have n squared, that is 3 squared, times 2 to the n, times x minus 1 cubed, over 3 factorial. We need one more term. I'll put it down below. So when n equals 4, we have -1 to the fourth, which is positive, and then n squared, 4 squared, times 2 to the n, times x minus 1 to the fourth, over 4 factorial. Given this, what is an upper bound on the error given by the expression absolute value of f of 1.5 minus t sub 3 of 1.5? Now, upper bound is a clue that we're doing the error, but so is this expression. So recall that this part, f 1.5, is the actual value of the function. Then we're going to subtract off t sub 3 of 1.5, which is the approximation using the third degree polynomial. We're centering our polynomial at 1, and we want to find the value at 1.5. So what is the error? Well, the error using our third degree polynomial approximation is no more than my first left-off term. So my first left-off term is 4 squared times 2 to the fourth times x minus 1, but x is 1.5, so 1.5 minus 1 to the fourth, all over 4 factorial. And I simplified this earlier and got 2/3. Feel free to check me just to make sure I got that number correct. So the error when using my third degree polynomial approximation to approximate the function at 1.5 is no more than 2/3. One more example. Let f of x equal 1 minus x plus x squared minus x cubed over 6 plus etc. And you may make two assumptions here. You may assume that the series alternates and that the series converges to f for all x values. Using the second degree polynomial approximation, what are the most appropriate bounds on f of 1? Well, let's start by approximating f of 1 using our second degree polynomial. Notice that the series is centered at 0, so we're going to find a value or approximate a value close to 0. Which means we will plug in x equals 1 up to the second degree term. So 1 minus 1 plus 1 squared, which equals 1. So right now, I think that f of 1 is about 1. But I'm pretty sure there's an error associated with it. In fact, I know there is. So the error, using my second degree polynomial, is no more than the first left off term. Where the first left off term is here, I don't need to worry about the negative sign because of the absolute values. And when I plug in 1, I get 1 cubed over 6. So what are the most appropriate bounds on f of 1? What does that mean? Well, right now, my best guess at f of 1 is 1. But I know that I'm no more than 1/6 away from my guess. In fact, in either direction. So as it stands, I have that good bounds on f of 1 are somewhere between 5/6 and 1 plus 1/6. You'll see why I didn't simplify that yet. Now, I would argue that these are not the most appropriate bounds on f of 1. I would argue instead that I don't need that. Here's why. If you recall how we were doing the sequence of partial sums on a number line, so the sum of the first term is 1, and then I go back, and I'm going this way, right? Going back and forth, and I'm getting smaller and smaller and smaller. So notice here that when I use the first few terms, I went positive, then negative, then positive. Now the first left-off term is negative, which means when I went positive and then negative and then positive, that is the biggest that f of 1 could possibly be. Because the next term I'm subtracting, which means I wouldn't need to go above 1. I could just leave my upper limit as 1. So the most appropriate bounds on f of 1 are these.